Okay, second way to find the rate law. I wrote on the board, you can see I added to the list. Our first way was finding mechanisms. How do we find a rate law using a mechanism? What do? Go to the slow step. Take the reactants. Raise their concentrations to the coefficient. However many are in the slow step is what the order is. So if you have 2 molecules of something, it's second order. If you have 1 molecule, it's first order. Okay? That's how you do it with mechanisms. Today we're doing it mathematically with experimental data in something called method of initial rates. So what I want to just focus on for a half a second is for you to pay attention to what data you need to actually do this process. I've seen students try to do this process on sets of data that had nothing to do with this. So just know that you need to have different experiments where somebody varied the concentrations or the initial concentrations of the reactants, and at the moment they put the reactants together, they measured the initial rate. Okay, so these different experiments were completed, and from this data, we're going to be able to find what that what that rate law actually is. Now, the person that did this was very strategic in what concentrations they chose. This is based on keeping at least one of the reactants constant for 2 of the experiments, because in doing so, if you notice, experiment 1 and 2, those in the real world, that's constant, pretty much. Keeping these constants and only having a change here is going to produce a change here. See how that's changed, that rate changed. Because we kept the F constant, we now know that this rate changed strictly because of the concentration change in NO. We're taking F out of the equation for those 2 experiments. So strategically, they picked certain concentrations to use. All right? So what we're going to do, the first thing is we're going to do in this example, if you took pre-AP, we did this. We're going to do the ugly algebra method to find it. This year, I'm going to teach you a shortcut to top on to that, and you get to choose whichever way you want. There's pros and cons to each. Neither way is right or wrong, so I'm going to let you guys choose. So the first step of this is always to write the skeleton of the rate law, because what you're going to do in ugly algebra is plug into that rate law. So you're going to write rate is equal to the rate constant times your reactants. You've got NO2. Do we know what the order is yet? Nope. So we're going to call it X times the concentration of F2. We don't know what that order is, so we're going to call it Y. So that's the skeleton. And our job will be to find the order with respect to NO. We're going to find the X, and then the order with respect to F2, we're going to find the Y. And then we're going to have enough information we'll be able to actually solve for the numerical value of the rate constant. First step, second step. This was the first step. Second step, pick 2 experiments where the concentrations of at least 1 were held constant. Which ones do you want to do? 1 and 2. Okay, so we're going to basically, the big picture, we're plugging in the variables for each experiment and we're dividing one by the other. That'll make more sense when you actually see me do it. But because experiment 2 has a bigger rate than experiment 1, I'm just going to put experiment 2 on top. I think that's a smart move. Oh, no, wait. Experiment 1 is up bigger. My bad. We're going to divide 1 divided by 2. That whole exponent thing threw me off. Math is hard. All right, so you'll see why I did that when we get to the math. So this is easy. You're going to take everything from experiment 1 and plug it into this rate equation, leaving things we don't know as they are. Rate, oh, we know rate. I'm having a really dumb day, folks. One of those days. So we're going to do 1 divided by 2. Our rate of experiment 1 is 1.90 times 10 to the negative third, and that's equal to, we don't know K. In experiment 1, the concentration of NO2 is 0.0482. We still don't know the order, raised to the X. And then we're going to put in the concentration of experiment 1 of F2, 0.0318, and we don't know Y. Is this ringing a bell? Yep. And we're going to divide that by experiment 2. And that's a rate of 4.69 times 10 to the negative 4th equals K times 0.0120. We still don't know X, times 0.0315. We still don't know Y. So what we can do is actually cancel out things that are the same on top and bottom of this equation. It's like a ratio, basically. So we're going to, since this is numerically the same in both, we can get rid of it. What else can we get rid of? The Y stuff, all of this goes. So what we do now is we just divide 1.90 times 10 negative 3rd by 4.69 times 10 negative 4th, and tell me what you get. .05 is equal to, and what's 0.0482 divided by 0.0120? It's about 4. Is it exactly 4? .02 raised to the x. That x we don't get rid of. We leave it there. So in the real world, mathematically, what is that pretty darn close to? What is x? X is equal to 1. Now here's what I'm going to be a little bit harder on you this year than last year, and that's how you earn the point. If they want you to determine the order, they want you to assign. You can't just say this and be done. You have to then say, okay, now that I know this, I can confidently say that this is first order with respect to which reactant? NO2. That's what earns you the point. When they say explain, if they ask you to, well, when they say determine the order or to explain, you don't have to do anything beyond this because that math is your work. And that's what's kind of nice about doing the ugly algebra. You don't have to really talk. You don't have to explain because it's done so in what you've already shown. But you've got to then say this to get that point. You can't get the point without either this statement or the work. You have to have one. You have to have both. All right, y'all ready to try the next variable? I feel like a color change is in order. Let's do that color. All right, now we're going to pick 2 more experiments where the other variable or the other reactant is held constant, which would be what? 1 and 3. So I'm going to pick the one with the bigger rate just to make my math cleaner and put that on top. So I'm going to do 3 divided by 1. If you do 1 divided by 3, you're totally fine. That's not a big deal. It's still going to work. You have calculators. You can figure it out. It's just cleaner the other way. So experiment 3, rate is 7.57 times 10 to the negative 3rd equals 0.0480 raised to, you could put the x or you could put 1. It really, oh, we don't know. That was NO2. Never mind. Oh, that is NO2. Yeah, you could put x or 1 times 0.127 raised to the y divided by 1.90 times 10 to the negative 3. I forgot the k, equals k. The k's are going to cancel. Times 0.0482 raised to the 1 or raised to the x divided by 0.0318 raised to the y. So k's cancel. What else cancels? That whole 0.0482 to the first or 0.0482 to the x. So we get 7.57 e negative 3 divided by 1.90 e negative 3. .98 is equal to what to the y? 3.99 to the y. So this is a boring problem. That's okay. Boring is not always bad. So y then is equal to 1. So this is then first order with respect to F2. Okay, so now let's move on. Determine the overall order of the reaction. Because I say determine, I do want you to show, as simple as it is, you're going to add up your two orders. So this is second order overall. Okay? Now, write the specific rate law. Well, this is pretty easy. All you do now is plug in what we do know up to this point. We know that rate is equal to K times NO2 to the first times F2 to the first. And that would be accepted. A lot of students on the AP, you are capable of solving for K at this point. A lot of students will go and solve for K and then put the numerical value in there. And that's fine, but you're not required to do it because I haven't asked you to calculate it yet. The next question then is calculate the rate constant. Because they're asking that after this question, you really don't have to calculate the K yet. Now, if they would have swapped those and said determine K and then said write the rate law, you would have had to put the numerical value in. Okay? Does that make sense? They're not going to have you find K to do that and then ask you to calculate K. Their tests don't work that way. So let's go ahead and determine K. The way you determine K is, and this is just what I want you to do, you can theoretically take any experiment and plug in the two concentrations and plug in the rate and solve for the K, but the AP rubrics always have experiment 1 data on that piece of paper. I want you to use that because that's what they have the key for. If you use another experiment, we may have to plug the numbers in and check, and that just could lead, we might screw up, and we might see there's an error. So I'd rather you just, everybody use experiment 1. So you're going to plug experiment 1 data in. I can't see it anymore. What was the rate for experiment 1? What? I heard a lot of mumbling. 1.90 times 10 to the negative 3. And the units on that are molarity per second. That's equal to K times concentration of NO2. What was it? And that's going to be a molarity. And the concentration of F2? 0.0318. And that's going to be a molarity also. The reason I'm doing this is units are required on kinetics case. So in addition to solving for the numerical value, we have to solve for the units. So you guys are math savvy. You know you're going to take this rate, divide it by the two molarities to get K. So go ahead and do that, and to 3 sig figs, give me an answer. Yeah, 1.24. Okay, now you could do units the old-fashioned way. You could sit there and go, okay, in order to isolate K, I took molarity per second, and I divided it by a molarity, and then I divided it by the other molarity. And what does that get me? 1 over seconds times molarity. Now, that's fine and dandy. You can totally do it that way. But there's going to be some that we're going to do on Monday with when we graph the integrated rate law, where all you're going to have is the slope, and you're not going to have a rate law to actually work with. You're not going to have the units and all that kind of stuff. So it's good to know the shortcut. And I'm going to tell you what that unit shortcut is. The unit shortcut is 1 over your unit of time. To get the unit of time, you go to the table. It could be seconds, it could be minutes, it could be hours. You just have to look at the table. Times, now I'm just going to write molarity here, but in these tables, you can have pressure as well. You don't just always have molarity. So whether it's molarity or pressure, that goes here. and you raised it to 1 less than the overall order. So it's the overall minus 1. What was the overall order for this reaction? 2. So it would be 1 over seconds times molarity raised to 1 less than the overall order. So it's 1 over second molarity. Okay? In this particular problem, it's like, how is that any easier to do? But there's going to be times that this is going to be a gem, knowing how to do this. So I definitely want you to know how to do that. We'll do it again because the next one's going to be a little bit different. So this is the ugly algebra method. How do you feel about it? Okay, like it? All right, now let's go ahead and move on to table inspection. This is a way to do it where when the math, see how those numbers are cleaner? It's a lot easier to do it by inspection this way. And so when you do it by inspection, you don't even need to write the skeleton of the rate law because you're not plugging anything anywhere. All you're going to do is you're going to first pick 2 experiments where one thing is kept constant. What 2 experiments? Let's do 1 and 2. So if you look at 1 and 2, I'm going to cross that out because that was constant, right? So I'm focusing on H2 and the rate. As I go from here to here, what power do I raise it to get this change in rate? So let's look at what the change was. What happened from 150 to 300? That is doubled. What happened from 0.66 to 1.34? Doubled. Why is that? Are y'all okay? That's doubled. So the question is, what exponent do I raise this to get that change? 1. And so that's the answer. First order with respect to which one? Well, it's not pH2, it's H2, because these are just pressures. That's why the P is there. First order with respect to H2. It's okay, because someone said that last period, exact same thing. They went pH2? No, just H2. All right, here's the drawback to this method. That will not get you the point. You're going to have to explain why you came to that conclusion. So I'm going to write down kind of what you need to say. You got to kind of describe your process. As the pressure of NO was held constant, the pressure of H2 did what? Doubled. Doubling the H2 pressure made the rate do what? Made the rate double. Therefore, that's first order. If the pressure doubles and the rate doubles, it's first order. So that's what you would need to write to get your point. All right, let's do the next one. We're going to keep the other one constant. We're going to keep H2 constant. So what experiments? 3 and 4. These are constant. So what exponent happens to this in order to get this change? What did we do here? Doubled it. What did we do here? Quadrupled it. So what does that exponent have to be? It's 2. So this is second order with respect to NO. As the pressure of H2 was held constant, the pressure of NO doubled. Doubling the NO pressure made the rate do what? Quadruple. If you don't know the word quadruple, you could say increase the rate by times 4 or something like that. But quadruple is fine. So that is second order. Okay? So it's up to you to decide. Do you rather want to write, would you prefer to write this and do that, or would you rather just do the math? That's going to be up to you. What are y'all leaning to? Just curious. Okay, how many say this one? Interesting. This is more 50-50 than usual. Usual people are all over this one. And then the other one? Okay. That's just the type of personality you have. If you're like, you got to do the other way. But if you're more like, yeah, I'm going to go with the flow, I'm just going to write it out, that's kind of that. All right. So this next problem, I'm not going to do this for you. Oh, wait, we're not done yet. Sorry. It's called Friday. Why are you doing this to me? No, close. Oh, come on. Y'all, I don't know how to get rid of this without doing something crazy. No, no. Okay. All right, we need to continue and we need to determine the overall order. What's the overall order? So 1 plus 2, third order overall. I mean, it does say determine the order. That's the thing that you really need to be careful with on the AP. If it just says, what's the order, and you say third, we can't make you show any work. We can't. But because it says determine, they could technically hold your feet to the fire and expect to see that 1 plus 2. It's kind of crazy, but that's how it works. All right, write the specific rate law. So rate is equal to K. Now, oh, this is another thing you got to watch for. You can't use brackets. It's pressure. Brackets indicate concentration. And there are some of those professors at the reading who are like so hung up on those little details that they could nail you for it. So if it's pressure, you're going to use parentheses, and we have the pressure of H2, and we have the pressure of NO. What was H2's order? I don't remember which one was 2. H2 was 1 and NO was 2? All right. And it doesn't matter what order you put those two in, but make sure you couple the correct order with the correct thing. Okay, and the last thing is determine the rate constant. So using experiment 1, what was the rate? 6.6. Now we've got millimeters of mercury instead of just plain old concentration. H2's concentration? 400? We're going to pretend that's 3 sig figs. To the first, and then NO's? The NO's 400? Okay, which one's the H2? 150 to the first, and this is 400 squared. So go ahead and give me the numerical value of K, and then we're going to use the shortcut on the units. Give me 2 sig figs. 1 point what? Times 10 to the negative 8th? Negative 5th. What did y'all, I don't remember this answer. And okay, 2.8 times 10 to the negative. That sounds like last period. Okay, let's do the shortcut. 1 over, what was my unit of time? Seconds times, it's not concentration this time, it's millimeters of mercury, raised to 1 less than the overall. What's the overall? 3, so 1 less than 3 is 2, and those are the units. Just know that in your homework, one of the questions wants you to do the units on a 0 order reaction. So it would be 1 over your, say we're in seconds, unit of time. What's 1 less than 0? Negative 1. So that's correct, but how can we simplify that? Yeah, so this is 0 order. So you can, that is possible. Okay? All right, so This next problem I'm not going to do because it's really beyond the scope of kind of the problems we see. I foresee you having a method of initial rates problem. I don't foresee you having one with 3, but it's a fun challenge problem. If you are like a stud and want to try it, go for it. I can help you with it if you're interested, but I'm not going to use class time for it. I will tell you that the 3 orders you'll get a half order, you'll get a 1 order, and you'll get a 2 order. What's with the half order? We're going to cover this when we get to equilibrium, but a half order, people are like, that doesn't make sense. You said order was how many molecules are in the slow step of the mechanism. How can you have a half a molecule? That's correct. That doesn't make sense. But what it's based on is in the mechanism, there's a step prior to the slow step. That's an equilibrium step. So that causes a proportionality between the products and reactants of the first and the reactant in the second, which we'll talk about in equilibrium. Don't worry about it. I just want you to know that this is a possibility. So if you want to try this and stud it out, do it. Give it a try. The starting point is these two. Got to start here because you're keeping a constant there and there, so you're solving for the order of that one. And then I'd be curious to see if y'all can figure it out. You can do it. It's definitely possible. So the last little thing I want to do, how many of you guys are in calculus right now? Okay, about 6 of you. I'm sure some of the people that are absent are in calculus. I just want to talk about this in kinetics, and this is not something that they test over on the redesign much, but it's something that I think is interesting. I want to make some connections to all that math that you do, and you're like, there's no real life connections. Why am I doing this stupid math? Well, this is a prime example of when the math you're doing applies. This is called finding the instantaneous rate. So as I start a reaction, I have a high concentration of reactants, and then as the reaction progresses, we all agree the reactant concentration drops, right? So it creates a curve that looks like this. So as the reaction progresses, concentration of reactants decreases. If I wanted to know the actual rate of the reaction at a certain time, I would find the instantaneous rate. So let's say I wanted to find at, looks like 8 minutes. 8 minutes, what is the rate at that point? Well, we know that this is concentration and this is time. So how do we measure rate? Remember that first day? Isn't it change in concentration over change in time? Isn't that rate? What on this graph represents change in y over change in x? The slope. So what you do is at the point of the curve, at that 8-minute mark, you draw a line tangent to the curve at that point. The slope of that line is the rate at that point. That's called instantaneous rate. There is a thing in calculus that represents this. What is it? Derivatives. So when you find the derivative of something, that's what you're actually doing. What I find interesting is looking just at the slope as the reaction progresses. Up here, it's a really, really steep slope, right? At the beginning of the reaction, that's when your reaction is the fastest. And so as the reaction progresses, and I'm just going to use my pen, people at home can't see it, the slope starts to get less and less and less as it progresses, which is what happens to the rate. So anyway, that's a real-life connection so you understand why you do things. And when you get to physical chemistry, P-Chem in college, which is the worst class I've ever taken, you use calculus. I had to use, I don't even remember. All I remember is thinking to myself, I am using calculus to find the boiling point of water. Like integrals, I was like, what am I doing? It was horrible. But anyway, there's a definite need for calculus in advanced chemistry. So, all right, you can get started on your homework. That is it. We'll do the third way on Monday.